Let's go live. Awesome. I think we're live. Sorry about that little delay, everyone. Welcome to this week's free Sherpa lesson. It's going to be on maths, it's going to be on geometry, and it's going to be by Ollie again, fan favourite from last time. So, Ollie, over to you.
Thanks, James. Yeah, so this lesson I thought it'd be good to focus on kind of length, area, and volume, and kind of how scale factors and sizes of shapes basically change as you kind of go through those 1, 2, and 3 dimensions. It's one of the things that all my students tend to stumble on when they first come across it. It's not entirely intuitive. And we're gonna kind of derive some kind of general rules first, and then apply these rules to a couple of kind of exam style questions later on. So first of all, we are going to look at area. So if I give myself a nice title here, area, I'll call this area scaling. And we'll do a nice example to start off with. So if we just look at, say, a square, and I'm going to say this square is 1 centimeter by 1 centimeter. And we're going to look at what happens to the area if I increase the size of my square. So I could draw another square, and let's say I want to have a scale factor of 2, kind of a linear scale factor of 2, going from my first square to my second square. So I'm basically going to kind of have a times 2 scale factor. And if you kind of imagine, well, what are the lengths going to be? Obviously, this length is going to be now 2 centimeters, and this length is also going to be 2 centimeters. And you can probably tell me the area of the square is going to be base times height. It's going to be 4 centimeters squared. So nice and straightforward. And this is obviously 1 centimeter squared. And another way of kind of intuitively understanding this is you could say, well, how many times can we fit this original square into this new square? If I get rid of this for now, give myself some space inside here, we can basically fit it in 4 times, can't we? We can kind of fit that original square into our new square 4 times. And so we get our 4 centimeters squared area. And we could do one more. We could do the same thing again, and we could look at a 3x scale factor, and you'll probably start to see the rules appearing. So I'll draw an even bigger square. Hopefully I've got just about enough space. And again, we could see we've got we've got a 3 by 3 square essentially. I could draw in a kind of grid system to kind of make that super clear. And again, it's going to be 3 centimeters base and 3 centimeters height. And base times height gives us an area of 9 centimeters squared, which again is what we'd expect, right? Because slightly weird too there, because obviously we can fit our original square into our new square 9 times, as we can see from this kind of grid going on. So that's the kind of basic basic intro to what is happening with area as we have our linear scale factor come into play. So if I was to kind of summarize what's going on here, I've got my linear scale factor. I'm just going to call this scale factor, my kind of base scale factor. Well, when this is 1, I end up with my original square. When I multiply this by 2, my area becomes 4 centimeters squared, and when I multiply it by 3, my area becomes 9 centimeters squared. So this is my kind of area scale. And you could probably guess, if you've spotted the pattern, what would happen if we had a scale factor of 4 between our shapes. Because as we can see from these first three numbers, 1, 4, and 9, these are special numbers and they are square numbers. So we could kind of continue this nice pattern on and get a few more numbers in there. And it makes sense that they're square numbers, right? Because we're literally doing whatever our scale factor is, we multiply it by itself, right? We do kind of base times height, and that gives us that square number. It gives us 2 squared. Again, we do on this larger square, we do base times height, and that gives us a larger area. So we're always kind of squaring our linear scale factor to get our area. So that's why we end up basically squaring our scale factor to get our area scale factor. We could do a similar thing again, and we could look at volume as well. So if I go on to, I'll go on to a new slide. Also, another nice example of area. Just before we touch on volume, I could have, say, a circle and a bigger circle and an even bigger circle, and I could have, say, a radius of 1, a radius of 2, and a radius of 3. And hopefully you'll remember your formula for the area of a circle is pi r squared. Well, in this case, to get from my original circle to my new circle, my slightly larger circle, I have to double my radius, right? So I'm going to be ending up doing pi times 2r squared, which gives me 4 pi r squared. So this is kind of 4 times the original area of my smaller circle. And I could do a similar thing again to get to my much larger circle. I have a scale factor of 3 because I'm going from a linear radius of 1 to my linear dimension, my radius of 3. And again, I could calculate the area. So I could do pi times, in this case, it's 3r squared because I'm tripling my radius from 1 to 3. And that then gives me 9 pi r squared. So again, we can see we've got this kind of 1 pi r squared here, 4 pi r squared, 9 pi r squared. We have that same 1, 2, 3, 4, 5, our kind of scale factor, and we end up with these square numbers appearing. And I could fill in the rest. I'd get my staying kind of 16 and 25. So that's how we can kind of relate our linear to our area scale factors. Right, I'll go on to another page and we'll do some area now. So we've seen area. Area is squared. Volume, you may guess, if area is squared, volume is going to be a cubed relationship. So I'm going to attempt to draw in some cubes. We'll see how it goes. I draw a small cube, a bigger cube, and a bigger cube still. And I'm going to separate this up and make it kind of 3D-ish. Hopefully that's not too poor. I didn't do particularly well in my GCSE art, so apologies in advance. I was too busy doing maths. All right, I think we're there. So as we can see, we're kind of making our bigger cubes out of kind of multiples of our smaller cubes, right? We're kind of combining this base cube that we've got over here, and we're kind of making bigger and bigger cubes, kind of like Rubik's cubes in a way. So if we, I'll just make that 3D as well, just to finish it off. If we wanted to kind of calculate what's going on with the volume now, well, I want to make it super easy for myself. And I'm going to say this is a 1 centimeter by 1 centimeter by 1 centimeter cube. And so obviously the volume of my cube is going to be base times height times depth. 1 times 1 times 1 gives me a volume of 1. And the units, because I'm doing centimeters times centimeters times centimeters, are going to be centimeters cubed this time. We could do a similar thing again for our larger cube. So my linear scale factor, right, is going to be a scale factor of 2, isn't it? Because I've now got a kind of base of 2, a depth of 2, and a height of 2. So I'm kind of multiplying my original cube by a scale factor, a linear scale factor of 2. And there's kind of two ways we could calculate this. We can use our standard formula, which is base times depth times height. 2 times 2 times 2 will give us 2 times 2 is 4, times 2 is 8. So that's one way I can get my volume of 8 centimeters cubed. The other way is we could just literally count the cubes, right? How many lots of 1 centimeter cubed cubes do we have? Well, we've got 1, 2, 3, 4 in the first layer, and we've got another 1, 2, 3, and there's one kind of at the back there, or in our second layer. So again, we've got kind of 8 of our mini cubes to make our larger cube. And that's why I've kind of divided these up into smaller cubes to kind of make that clear. We could do the same thing again and look at our even larger cube. Well, we're now going from a linear scale of 1 by 1 by 1 to a linear scale of 3 centimeters by 3 centimeters by 3 centimeters. So our linear scale factor is going to be 3x, isn't it? So we could do both methods just to make it super clear. Our volume of our largest cube is going to be base times depth times, or kind of width times depth times height, and that's going to be 3 times 3 is 9 times 3 is 27. And again, those units are centimeters cubed. The other way we could do it, if anyone was super lazy and they forgot the formula for the volume of a cube, we could just count how many little cubes we have, right? Because each one of these little cubes, as I said before, is a kind of 1 centimeter cube. So I could pick a random cube on the corner here. This has a volume of 1 centimeters cubed, right? So however many of these little cubes we have is going to tell us what the volume of my large cube is. And we've got kind of 3 by 3 in this first layer. So all these cubes here in this kind of front layer, these have a volume of 9. I'll get rid of that. These have a volume of 9. We've got 9 cubes in our first layer. We've got 9 in our second layer, 9 in our third layer. So we've got 27 small cubes in total. So that kind of that's another way of thinking about how our volume is actually being calculated. And as you may already have spotted, as we increase our linear scale factor, as it goes from 1 to 2 to 3, our volume scale is, well, obviously it's 1 for our first cube, and then when we have our linear scale factor of 2, our volume scale factor then becomes 8. We have that 8 there, and for a 3x linear scale factor, we end up with a 27 centimeter cubed volume. So we're going from a 1 centimeter cubed for our small cube up to a 27 centimeter cubed for our larger cube. And hopefully you can spot the pattern. If I was to fill in another one, if we imagined a much larger cube off the screen over here, some of you might be able to instantly tell me what the volume of that cube would be. These are all, these are all our cubic numbers. So just like we had square numbers before, these are our cubic numbers. And 4 cubes is going to be 4 times 4, 16, times 4 is 64. It's always good to have a few cubic numbers in the back of your mind. And I could do one more. 5 cubed is going to give me 125. And we can see, right, it kind of makes sense why we're getting cubic numbers here, because we're literally taking our scale factor of 2, and that's giving us our length of 2, and also our width of 2, or our depth of 2, and our height of 2. And we're doing 2 times 2 times 2 to get our volume. So we're literally doing 2 cubed to get our volume. And same thing again, we've got our linear scale factor of 3. That gives us a kind of width and depth and a height of 3. we do 3 times 3 times 3 to get our volume. So that's why we end up with these this kind of a series of cubic numbers. So that's a kind of brief intro to how a linear scale factor will then impact our volume. We can now put this to the test. I've got a few kind of examples of exam questions that involve this kind of thinking. So we could have a go at solving some of these. Hopefully this comes out clearly. I might slightly enlarge it. It doesn't need to be that small. Right. So for question 1, we are told we've got 2 solid shapes, A and B, and they're mathematically similar. For anyone who doesn't know what mathematically similar means, or if you forgot, it just means they're the exact same shape, but they're different sizes. So all we've done is we've kind of scaled up A to get to B, but we haven't changed the shape of it at all, just the size. So we're also told that the base of shape A has a radius of 4, and the base of shape B has a radius of 8. That's just kind of explained to us in the diagram there. And the surface area of shape A is 80 centimeters squared. So we want the surface area of shape B. Well, there's kind of a couple of different ways we could think about solving this question. We just from looking at these 2 shapes, we can already work out what the linear scale factor is between them, can't we? Because if we look at how the lengths are changing, well, the first length is 4 centimeters, the new length is 8 centimeters. So I know my linear scale factor is going to be 2. I'm kind of multiplying all the lengths by 2. For example, if this was a length of I don't know, 5, then this would have a length of 10. Just as an example. So all of my lengths are going to be multiplied by that same scale factor of 2. And we can now look at how does that then affect our surface area. So we know from our previous learning that if we are told what our scale factor is, we can then square that, and that will give us our surface area scale factor. So just like when we were dealing with squares and larger squares, the exact same thing applies here. We're just dealing with area, and the exact same rules apply. So if our surface area of A is 80 centimeters cubed, we now need to work out, what do we times that by to get the surface area of B? Well, my area scale factor is going to be equal to the linear scale factor, which is 2 squared. So it's going to be 2 squared, which is 4. So all of the areas in my new shape are going to be 4 times the areas of my original shape. So I can take this 80 centimeters squared, which is the total surface area of shape A. I can take that 80 and I can multiply it by 4, and that'll give me my new surface area, which is 320 centimeters squared, because the area is always going to be centimeters squared. And that's my answer to part A. Part B, we're told the volume of shape B is 600. Work out the volume of shape A. So we've already kind of learned how volume scales with our linear scale factor, haven't we? We know it always scales with the cube of our linear scale factor. So we could just apply that same learning to this question, and if my linear scale factor is 2, I can work out my volume scale factor. And that's just going to be my linear scale factor cubed. So obviously that's going to give me 8. We have to be careful though, because we're told the volume of shape B, and we want to work out the volume of shape A. So we're actually kind of going back in the reverse direction. So we're going to take our volume of shape B and we're going to have to divide it by 8, and that will give us the volume of shape A. So we'll do 600 over 8, and that'll give us shape B. 600 over 8. I don't want to mess this one up. I'll get my calculator out just to double check. I get this correct. 600 over 8, and we get 75. And again, we're dealing with volume here, so that's going to be centimeters cubed. So that is my answer for part B. Hope that all makes sense. We can try another couple of questions as well to kind of really solidify this theory. So if we go on to question 2, we've got two cylinders, A and B are mathematically similar. So again, they are the same shape but different sizes. And the height of cylinder B is twice the height of cylinder A. So we're given the linear scale factor, right? If this was height h, then this has a height of 2h. So we're also told the surface area of A is 180 centimeters squared. Calculate the total surface area of cylinder B. So very similar to question 1. We know our surface area of cylinder A. We know our linear scale factor. Scale factor is equal to 2. And so our area scale factor, I think they're being quite lazy with this worksheet because they've used the same scale factor twice. Our area scale factor is going to be our linear scale factor squared, which again gives us 4. And so we can take our original surface area of cylinder A, which is 180, and we know we're going to be scaling that by 4. So that would give us 360, 720 centimeters squared. And that would be our answer to question 2. So you're probably starting to see that most of these questions are fairly similar. Question 3, I may leave until the end if we have time, because this is actually not to do with scaling. This is just taking away one volume from another volume. So it's not particularly relevant to this topic. I might come back to that later. Let's go on to question 4. So cylinder A and B are similar again. Very similar question as well. The length of cylinder A is 4, and the length of cylinder B is 6. The volume of cylinder A is 80 centimeters cubed, and we want to calculate the volume of cylinder B. So first of all, we need to work out what is our linear scale factor. You know, what are we kind of multiplying this original shape by to get our new shape? And if we're going from 4 up to 6, we basically have to think, 4 times something, our scale factor, is going to give us 6. We could either rearrange this. I could say 4 times s is equal to 6, our scale factor, and so s is equal to 6 over 4. Or you could just spot that our scale factor has to be 1.5. So yeah, 6 over 4 is the same as 3 over 2. I may leave it as a fraction for now, just to make it easier when we end up doing our squares and our cubes. So we've got our linear scale factor equals 3 over 2. And now we're dealing with volume, right? So our volume scale factor, we're going to take our linear scale factor of 3 over 2, and we're going to cube it to get our volume scale factor. And we could do that quite easy. So 3 cubed, we saw previously, is 27. Always good to have that in the back of your mind. And 2 cubed is 8. So that is the volume scale factor. And so we can now work out the volume of B, right? So we're told the volume of A is 80. And we just need to do 80 times 27 over 8. and that'll give us our new volume of cylinder B. I could be slightly lazy about this and just cancel out some stuff. So I know this 8 is going to cancel out with that 8, and that will just become a 1. So I end up doing 10 times 27, which gives me 270. And that's going to be centimeters cubed. So that is going to be my answer. Didn't need to do it all the way over there. That's better. Yeah, so it's all these questions is almost the exact same thing every single time. We calculate our linear scale factor first, and then we just either square it to get our area scale factor, or we cube it to get our volume scale factor. There may be one more. Yeah, let's have this one. This might be a slight curveball, so good to finish off on a particularly nasty one. We've got X and Y are two similar solid shapes, so we know they're same shape but different sizes. And we're told the total surface area of X is 450 and the surface area of Y is 800. And we're also told the volume of X is 1,350 centimeters cubed. Calculate the volume of shape Y. So there's going to be a couple of stages to this one, right? Because at the moment, we aren't given a linear scale factor. We aren't given even how the linear lengths relate to one another. We're actually thrust straight into this question with being told what the area scale factor is, or how the areas relate to one another. So we're going to have to kind of work backwards to work forwards. You know, if you kind of imagine it on like a as a kind of a ladder, right? We've got linear down here, and then we've got area up here, and we've got volume at the top. And it's very easy to get from linear to area to volume, right? We take our linear and we square it. You know, I could call this x. I end up doing x squared to get volume and x cubed to get x squared to get area, x cubed to get volume. It's slightly trickier when we're told to kind of start off at area. It's not that easy to get from area straight up to volume, right? Because we're kind of given an x squared and we want to work out an x cubed. I'd say the easiest way of doing this is going from area, working out what our linear scale factor is, and then cubing that linear scale factor to get our volume scale factor. I might just do this in a slightly different color to make it clear that that's the kind of that's the path we're going to take to get from area up to volume. We're kind of going to go via linear and then up to volume, if that makes sense. Otherwise, we end up with indices with fractions in them, and some of you will be very comfortable with doing, say, x to the 2 over 3 or x to the 3 over 2. It would be for this one, but I'm going to avoid that for this one, and we're going to keep it fairly straightforward. So first of all, I can work out my area scale factor, can't I? So I've been told the area of x and y. And so if I want to get from, say, x up to y, my area scale factor is going to equal, well, I can imagine, what do I have to times x by to get to 800? I could think of this as like, I could think of this as like 450 times my scale factor is going to give me 800. And so my scale factor is just going to be 800 over 450. And I'm going to be super lazy and just do this on a calculator because I don't want to make a maths error live on YouTube. 800 over 450, that gives us 1.78 equals 1.78. And that's my area scale factor. So I could write it up here, 1.78. I could keep it as a fraction, but I'll leave it as a decimal for now. I did fractions last time, so we'll do decimals this time. So if that's my area scale factor, and I want my linear scale factor, well, I know the area scale factor is the squared version of my linear scale factor, right? So how do I get from this kind of x squared back down to x? All I do is I do the opposite, right? So I know I square linear to get area. So to get back down to linear again, I've got a square root. So my linear scale factor is going to be equal to the square root of my area scale factor. And I could shove that into my calculator, and I end up with square root of 1.77. I get 1.33 recurring. I've got it 1.33. And that is my linear scale factor. So now, if I want to now focus on the final part of this question, and I want to work out the volume, so we're told the volume of shape X, and I want the volume of shape Y. All I do, probably guessed, is to get from my linear. So I've done this first bit of my journey, right? I've kind of gone from area down to linear. I now need to go from linear up to volume, and we've seen before that we just square our scale, so cube our scale factor, and that allows us to convert our volumes. So in this case, I'm going to take my linear scale factor, 1.33, and I'm going to cube that number. And again, I'm going to just do it on here to save time. I'm going to do 1.333 times 1.333. I'm on a phone calculator, so don't have the luxury of a key button, unfortunately. So we end up with 2.37. And that is our volume scale factor. So the very final thing that we need to do is, now that we've got our volume scale factor, I'll just kind of make a note. This is my volume scale factor. We're going to take that volume scale factor and multiply my X volume, which is 1,350. So I can take that, multiply 1,350, and my answer is 1,350 times 2.37. It's going to give me 3,200. And that is my final answer of the volume of shape Y. And obviously the units, because we're doing a volume, is going to be centimeters cubed. They've been nice enough to give us the units already. So sometimes they're mean and they don't give you the units and they expect you to do it. I think especially in physics, with physics questions, you have to be wary of that. But this time we can just plug in our number down there. And that's it. That's all the questions we've probably got time for. There's a few more if anyone has any questions or wants to do more examples. But I think for now that's half an hour. So yeah, up to anyone else if they want to see any more.
That was excellent. We do have a couple of questions, so I hope you're strapped in and ready to go again.
Okay.
So the first one is, can you show us how to calculate the area of a sector? I don't think you touched on this. I had a quick look through the guidebook just to see what it was. I'm assuming, having seen it, it's a sector of a circle, but again, that's up to interpretation.
Okay, yeah, I'll go on to a new slide. So I think, wait, let me just get my circle up. And so if we're talking about the area of a sector, I guess we're talking about something like that, like a pizza slice, right?
I would assume so, yeah.
So, and we want to work out what is the area of this shape here. So, I mean, there's, depends what information you're given in the question. the nicest way of calculating this is, if you imagine for a second, uh, I've just asked you to calculate the area of the whole circle. So we're going to start off by calculating the area of the entire circle. You would tell me, oh, I'm still stuck on there. And you tell me the area is equal to pi times r squared, right? That's our kind of standard circle equation. And if we then wanted to work out the area of like a small segment, well, imagine I could have told you we have to kind of define what the segment is. So we could say the angle of this small segment is, say, 60 degrees. And if we kind of compare this segment we're looking at to our whole circle, there's kind of two ways we could do this. Well, I know that 60 degrees is going to be 1/6 of 360, right? So I know this is kind of 1/6 of my entire circle. The mathematical way of doing this is we take our angle, we take this kind of 360 degrees, and we do 60 over 360, and we get, we can simplify down, divide both sides by 10 first of all, that's 6 over 36. Again, I got a common factor of 6, so I end up with 1 over 6. That's how we could calculate it kind of formally. We work out what fraction of our total circle we're focused on, and then we take our total area, and then we just multiply it by that fraction. So in this case, the area is going to be 1/6 of pi r squared. We could do a nastier example. I could have I don't know, I could have another circle. Let's do a little circle over here. Um, Again, I could have a segment that maybe looks like that, and I want to calculate this area. Again, we need to be told either what the angle is, I can be told what that angle is, and therefore I can work out what that angle is. It's just 360 minus that angle. Or we could be told, say, the radius. I could be told, that radius might be equal to 5, and I could be told, well, what's the length of that arc around there, for example. And again, once we found, if we were told this could be, let's say it is 7 pi, right? That length there. And I know my total circumference is going to be pi times diameter, isn't it? That's our kind of standard formula for circumference. So it's going to be pi times diameter, which is pi times 10, because my radius is 5. And so if my total diameter, my total circumference, sorry, is 10 pi, and I'm interested in the bit that's subtended by 7 pi, I can work out the fraction of my circle again, can't I? I can say the fraction of total, something weird, of total circle is going to be equal to my bit of circle that I'm interested in divided by the whole circle, which is 10 pi. And the pi's cancel out, and we end up with 7 over 10 as the fraction of my circle, which looks about right, doesn't it? It's about kind of 70% of my circle. And again, we just take that fraction, that's the kind of fraction of the circle that I'm interested in, and I multiply my total area by that fraction. So I would take my original area, which is always going to be pi r squared, and I would multiply it by 7 over 10. In this case, r is 5, so we'd end up doing 7. Oh, we'd end up doing 7 times 25 over 10 times pi. I've just taken that r squared and kind of put it over there to get that 25, just to kind of group all my numbers together, and that would be the area of this kind of this bit of our circle that we're interested in. So yeah, there are kind of a couple of examples of the kind of questions you might get in terms of finding areas of parts of a circle.
Awesome. Every time I hear pi r squared, there's a YouTube video that goes through my head. Pi r squared sounds like area to me. If you haven't watched that YouTube video, I'd recommend watching it because it will stick with you for life. Next question. Can you use a higher scale factor for the second question, please? Are we able to
If I
go
go
back
back
to
to
that
the
one?
second question, I guess question 2 is this one here.
They don't give. They just say for the second question. So I would
Okay,
assume
I'm
that's the
guessing they mean
second one you
question
got
2.
to. Yeah.
I think I did. Yeah, I'm assuming it's not these ones. So
No, yeah, I
I'm
would
gonna go
assume
on to
it's that
question
one. Yeah,
2.
yeah.
So yeah, so if we wanted a higher scale factor for question 2, yeah. So let's just say my scale factor is. I'll do it in a different color just to show us a kind of new thing we're doing. I'll go blue. So on the side here, let's say our scale factor is in fact equal to I'll test my maths. Let's go 7. My area scale factor, Well, again, as with all these questions, we just take our linear scale factor and we square it. Just like when we had our, you can imagine it like a square and a much bigger square. This has a sides of 1, and my new square has sides of 7. Well, this is gonna have an area of 1 squared, which is just 1, and this is gonna have an area of 7 squared. So that's why we end up squaring our linear scale factor. So in this case, my area scale factor is going to be 7 squared, which is 49, right? I might just write down it's 7 squared, which is equal to 49. And I'm going to take that scale factor, and I'm now going to calculate the area of cylinder B. So just like we did before, we calculated our scale factor, and then we multiplied the area of A by that scale factor. I'll do the same thing again. I'm going to take the area of A, which is 180, and this time I'm going to times it by 49. And this is going to be a calculator one. So we do 180 times 49 and went with 8,820. And that's going to be in terms of centimeters squared, because we're dealing with area in this case. So hopefully that answered the question. I can do a high one still, but it's always going to be the same principle. So we always just square our linear scale factor.
Yeah, I think I would assume they just wanted to see you try a little bit harder than the scale factor of 2. I would assume, but no, that's even I'm learning. It's reawakening.
I should have
stuff.
vetted these questions really before copying them in. Slightly lazy questions, I think, these ones.
Well, it's always good to start off with a platform. And so the last question we have is it complicated to work out the volume of a prism?
The volume of a prism. All right, I'm going to go on to a new slide. Let's go on to 13. No, not particularly. No. So we really need to know the volume of the kind of base of our prism, right? So a couple of examples. Let's say we've got a triangular prism. Well, all I really need to know is what's the area of my triangle, and then I'm going to take that area and multiply it by the kind of depth of my prism, right? So in this case, the volume of the triangular prism is going to be the area times the depth. Well, it's the case in all prisms really. And for my triangle, well, the area of a triangle is, hopefully some of you remember this, half base times height. And so I could have, say, a base of 5 and a height of 6. And so this is going to give me half of 5 times 6. Half of 30 would give me 15. So that would be my area, and then I just multiply that 15 by my depth. And let's say my depth in this case is, I don't know, 20. And so I end up doing 15 times 20, and that'll give me my volume, which is going to be 300, I'll call it centimeters cubed in this case. And it's the same thing again. I could have a well, circular prism as a cylinder, so I won't do that one. But I could have a a weird prism. I could have, say, a trapezium prism or something. It can be anything really to give me that same prism. It'd look something like that. If I was to draw in those lines at the back there. And again, all I do is I work out the area of my base, and then I multiply it by the depth of my prism. In this case, the area of a trapezium is also a good one to remember. It's going to be, if this is, you've probably seen it in textbooks before. If this is A, and this is B, and this is H, all we do is A plus B over 2 times H, and then we multiply that by my depth, which I'll call D. And that'll be the formula that I'd use in this case. So it could be, I don't know, 5 and 7, and a height of 4, and a depth of, I don't know, 8. And we plug in those numbers, we get 5 plus 7 over 2 would give me 6 times height of 4, and then we multiply that by 8. Well, that's just the same as 24 times 8, which gives me, test my muscle maths, 32 plus 160, 192, probably, centimeters cubed. So it's the same for any prism that we have. All we really care about is the area of the base of our prism, and then we just times it by the depth of our prism. It's the same as when we saw, we went from if we calculate the volume of a cube, for example, you can imagine we're basically taking the kind of base layer of our cube, which for kind of a 3 by 3 cube looks something like this. And we're kind of taking that base layer, which we know the area of. It could be, in this case, it's going to be 9 centimeters squared. If we kind of look down from the top, and then we can imagine we basically layer that on top of each other. So we layer like another layer on top of that, and another layer on top of that, and we end up with a cube that is 3 by 3. And so all we're doing is kind of stacking layers on top of each other. And that's the exact same thing we're doing here with prisms. We're kind of imagining we've got one layer of our prism when we start, and we just kind of stack those layers on top of each other. In this case, we're doing it 20 times. And that builds up our volume as we stack those layers on top of each other. So that's why we end up doing base times depth.
That doesn't seem too complicated. Okay, thanks for that, Ollie. Really appreciate it. I'm sure people got quite a lot out of that, and we're going to see if we can break it down into those individual questions as well. So if people come across them like that as well, hi. If you're looking to get a tutoring session with Ollie, he is free. He is available for sessions just like this. You can catch his profile in the link below, and clicking on that will take you straight to his Sherpa profile. From there, you'll be able to get in touch with him and organise some tuition sessions. If you're looking for an English tutor or a science tutor, then again, head on to the Sherpa website. We've got thousands of tutors there ready and available for you to have some sessions with. And if you're unsure and you need a bit of help, get in touch with our tutor experts, 01628 337 590. We'd be happy to help you out. But yeah, thanks again, Ollie. Really appreciate it. And see everyone later.